Chemical names and formulas. So the goals: review the important characteristics of covalent ionic bonding, compare and contrast molecules and compounds, apply rules for naming covalent molecular compounds, apply rules for naming ionic compounds, identify polyatomic ions, and identify and use polyatomic ions to form ionic compounds. So the first term we'll look at is molecule. So a molecule is the smallest electrically neutral, in other words, it doesn't have a charge, unit of a substance that still has the properties of the substance. They're made up of two or more atoms, either the same element or different elements that act as a unit. So for example, H2O, right? H2O we know as water. If I break up into hydrogen and oxygen, it no longer is water. So H2O, the molecule, is the smallest unit of water where it still is water. If I break up into anything smaller, it's no longer water. A compound is atoms of different elements that have combined chemically. And what do you mean by chemically combining? Is that you have a chemical reaction and you have a chemical bond that's holding them together. A molecular compound, a compound composed of molecules and are formed as a result of covalent bonding. Typically, two or more nonmetals typically have relatively low melting point and boiling points. And then we have ionic compounds. Compounds formed as a result of ionic bonding typically have relatively high melting and boiling points. So if you look at the two, ionic compound and molecular compound. So let's look at this and this. So the characteristics that we'd see typically, molecular compound typically have a, relatively speaking, low melting point and a relatively low boiling point. Contrast with this with ionic compounds. They typically, and of course there's always exceptions, but they have a relatively high melting point and a relatively high boiling point. So those are the big differences you're going to be seeing, right, between molecular compounds and ionic compounds. Chemical formula. Chemical formula expresses the number and kind of each atom combined to form the simplest unit of a compound. So water, I just wrote that, H2O, right? That's a chemical formula. It's showing you the types of elements that are in it. So H for hydrogen, oxygen, O for oxygen, and then the subscript 2 is telling me that there's two hydrogen atoms, right? And there's no, if it's one, like oxygen there's just one of them in water. You don't have to put the subscript 1. It's understood. And so think of something like methane, CH4, right? Carbon, there's just one of them. You don't have to write the 1. It's just understood. But hydrogen, because there's 4 of them, I have to write the subscript 4, indicating that it's there. And let's say glucose, which we've talked about in biology, C6H12O6. This is telling me that there are 6 carbons, there are 12 hydrogens, and there are 6 oxygens. And this is the smallest unit that still is glucose. If I break up into smaller pieces, it's no longer glucose. Expresses, and these are just some other examples. So octane, methane, aluminum sulfate, and water. And water is, and for some reason the definition, the name went over here, but the chemical compound water is actually dihydrogen monoxide, right? So dihydrogen is the hydrogen, and monoxide is the oxygen. A term that we talked about before is electronegativity. So electronegativity is a measure of an atom's attraction or pull on electrons. As we saw previously, it's important to determine the electronegativity, which will influence whether you have an ionic compound forming or ionic bond forming or a covalent bond. Okay, so we saw that previously. Now, I mentioned oxidation state, but we haven't really gone into it much detail, and it's something that you're going to see more of over time. Oxidation number, which is also called the oxidation state, is numbers assigned to the atoms in molecules that show the general distribution of electrons among bonded atoms. So, if you are looking at when two or more atoms are bonded together, they're either going to share electrons, valence electrons through covalent bonding, or there's going to be a transfer of electrons. The oxidation number is going to actually help show you what's happening to electrons, where are they going, who's sharing them. All right. Chemical bonding, right? So both oxidation numbers and electronegativity are important in chemical bonding. So chemical bonding, in nature, atoms with the exception of noble gases, remember that's group 18, they do not need, for the most part, to bond to meet the octet rule. They do not exist as single atoms. So all of the elements, except for the noble gases, they don't exist as individual atoms. So, example, even oxygen. We talk about oxygen in the air. Oxygen, right, is actually O2 in the air. So what you breathe in is O2. O, just single oxygen atoms, they don't generally exist in nature because they want to bond to meet the octet rule. They're too unstable. So this results in a more stable electron configuration that is more electrically stable. So you're always so anytime you write hydrogen gas, H, it's not going to be H2. They will be bonded together. Oxygen, nitrogen is going to be bonded to other nitrogen atoms. Or these elements can be bonded in other types of compounds. So oxygen, hydrogen, we saw earlier with the glucose, C6H12O6, right? These elements are all bonded together because that's more stable than the carbons being by themselves, the hydrogens being by themselves, or the nitrogens being by themselves. And two major chemical bondings include ionic and covalent bonding. So we previously talked about those, but let's review them. Ionic bonding, chemical bonding which occurs through the mutual attraction between positively charged ions and negatively charged ions. Okay, so during ionic bonding, you have the formation of oppositely charged ions, and this occurs through the transfer of electrons, and then they have opposite charges. So those oppositely charged ions, they're going to be held together through the mutual attraction of their opposite charges. And typically, ionic bonding is going to form between metals and nonmetals. An ion is a charged particle. So ions can be other than just individual or groups of atoms. They can be particles that just have a charge. But if we have an atom that has a charge, like H plus, right, Fe2 plus, those are going to be ions. A cation is a positively charged ion. And anion is a negatively charged ion. Metals typically lose one or more electrons forming cations, and nonmetals typically gain one or more electrons forming anions. As a result, ionic bonding forms between metals and nonmetals. So when we represent ionic compounds, we represent them in a formula using the formula unit. So the formula unit is the simplest unit indicated by the formula of any ionic compound, the ratio of elements depending on their charges. So NaCl, we use this one. NaCl is the salt that you is salt, table salt. So NaCl. If you recall, chlorine negative, sodium positive. So they're opposite charges, right? Sodium loses an electron to chlorine. Because of that, the chlorine is going to have a negative charge and the sodium is going to have a positive charge. That's what's holding them together. This is the formula unit. But if you were to look at salt, excuse me, and we'll see this, a lot of your ionic compounds, they're going to form crystals. So when you look at like a salt crystal, they have a cube shaped. And if you were to look at the molecule, sorry, the atoms in there, you would see sodium and chlorine, NaCl, that they're attracted to each other, but they form their structure in a. Okay, let's take a closer look at the salt crystals. So this is from the open chemistry book, and this is a chapter 7 that goes over ionic compounds. So this is showing you salt over here. So you have salt. Now, the green balls are chlorine. See right there, and the purple ones are sodium. Now, what you'll notice on here is that there's a link between the atoms. So this, you see this chlorine, right? The chlorine that's over here, it's bonded to the purple, so the sodium here, but also it shows it to the sodium here, and it also shows the sodium here. So what is that? Why is that? Well, we said that the formula unit is NaCl. And the reason that they're attracted to each other is because sodium has a positive charge and chlorine has a negative charge. Well, when you're talking about a whole bunch of sodium and chlorine ions together, they're attracted to each other. So this chlorine that's here, right, which we said has a negative charge, it's attracted to the positive charge here and the positive charge here and the positive charge here above it. So it's when we talk about the formula unit, it really is telling us the smallest ratio of the atoms of the atoms in a ionic compound, that it results in a net zero charge. In other words, the balanced charge. So sodium and chlorine in 1:1 ratio, the positive charge and negative charge cancel each other out. All right, and so this is showing you sodium here, and then they're both showing you the same thing. But when we talk about the formula unit, again, it's showing you the ratio of the elements in a ionic compound, because they're attracted to each other because of charges. And as long as they have opposite charges, they're going to hold together because of the attraction between opposite charges. So that's salt. And if you look at salt, I drew the picture earlier, but you'll see that all salt will have these crystalline shapes. And again, that's because of the bonding, the bonding that's occurring in there. If you take a look at salt, table salt, that you will find, in the kitchen, it will have that cube shape to it. Okay, so go back to this right here. So again, this is what I was showing you. This cube shape. That's the shape of salt, and it's a crystalline lattice, very stable, and that's why salt. It's fairly strong. They're bonded together. They hold together pretty well. All right, so ionic compounds in a solid state often form crystalline lattice, resulting in a specific geometric shape. And that's why if you look at salt, no matter the size of the crystal, it's going to have this cube shaped, whether it's microscopic or if it's large. Now, monoatomic ions. These are ions formed from a single atom. So let's look at some of these off to the side. So you will see in this table, and the table, it for some reason went onto the other side, on the other page as well. But you'll see group 1, right? These are monoatomic ions that are produced, right? Commonly produced. And then group 2, right? Individual monoatomic ions. Now, do they stay that way? No. They don't. They don't exist in nature individually, but they do because they want to bond to be more stable. And you notice on here that a great deal of these are positive monoatomic ions. So calcium, right? That's one that we've talked about before. Potassium, sodium. I think lithium we've talked about. Now, you'll see it's that group 1, it's a positive 1 charge. Group 2, positive 2 charge, and that's because they're going to lose 2 electrons. But then look over here at chromium in group 6, Cr3 plus and Cr6 plus. So in order to have a charge of plus 6, that means it has to lose 6 electrons. And these are not, when you lose that many electrons, you're producing a monoatomic ion that's not stable. And so it's gonna bond. It'll actually bond, so it forms. If it has a chance, it'll try to bond to form a chrome 3 because that's much more stable. And you can see iron. Iron has 2 charges it can have: Fe2 plus and Fe3 plus. And then you'll see Cu plus 1, Cu2 plus, and then Au plus 1, and Au3 plus, and Ag plus. So silver and gold and copper. Mercury, and this came out, for some reason the subscript didn't work on there, but Mercury has 2 common monoatomic ions, Hg2 2 plus, right? And then you have Hg2 plus. So these are 2 common ions. Now why? So this is going to be a little confusing. It shows that Hg2 2 plus, and because each mercury has a positive 1 charge, but they don't exist. It only occurs when they're in pairs, when they're bonded like this. Let's look at a couple more. Group 13, aluminum 3 plus, and then you have group 14. You have tin 2 plus, lead 2 plus, nitrogen 3 minus. So so far we've seen all of these positively charged ions, and now we have these negatively charged ions that we start seeing. So group 15 through 17. So nitrogen 3 minus, oxygen 2 minus, sulfur 2 minus. Remember, if you have something that has a negative 3, that means it gained 3 electrons. A negative 2, it gained 2 electrons. Negative 2, it gained 2 electrons. And then in group 17, we have these monoatomic ions with a negative 1 charge. So you have fluorine, chlorine, bromine, and iodine. Negative 1 charge. Why? Because each one of these gained 1 electron. Why do they only gain 1 electron? Because that's how it would achieve the octet rule. So if you look in group 16, they're going to gain 2 electrons because they have 6 valence electrons. They need 2 more. Nitrogen 3 minus. Why is it going to gain 3 electrons? Because it has 5. It needs 3 more. All right. Now we can name monoatomic ions as well. So you name them. So you have positive ions and negative ions. They're both named differently. So positive ions, which has or also is called a cation, you name the element followed by the word ion. So all these that we saw already, any positive one, you would name it by just adding the ion. So lead, Pb2 plus, it's called a lead ion. Tin, SN, 2 plus, it's just called a tin ion. And we know, and it's positive charge. Aluminum, Al3, right? If it has a charge, a 3 plus charge, it's called aluminum ion. Right? Plus 3. And you don't, okay? Now negative ions. So an anion, how are they named? Well, negative ion, anions, you drop the ending of the element and add the name "ide" to the end of the name, or say, add "ide" to the end of the name. So we've all heard of fluorine, but if it's a negative charge ion, that's your fluoride ion. So you probably have heard that because that's found in toothpaste, as well as they'll fluorinate water. So they put fluoride ions in there because it hardens the outer coating of your teeth. So the enamel, it hardens the enamel of teeth. Nitrogen, you just remove the end and add IDE. Okay, if we go back to here again, fluorine, what we do is we remove the ending, the INE, and replaced it with IDE. So you go from fluorine to fluoride. Again, nitrogen, you remove the OGEN, and added IDE to make it a nitride ion. Now, binary ionic compounds. So binary, bi means two. So these are ionic compounds composed of two different elements. Ions are combined in ionic compounds so that some of their charges are equal. So this is really the beginning of where we're going to start writing chemical formulas. So you will see here, what are we showing here? We're looking at the methodology of actually writing an ionic compound. So let me put them next to each other. I'm going to write it here like this. Mg, and we said it was 2 plus, and bromine, which is negative, and we just put a negative symbol there, but that if it's just a negative, it means that it's -1. And now if you want to write the formula, right, I want the charges to be equal. So there's 2 positive charges and 1 negative charge. In order to do that, I'm going to have 1 magnesium and 2 bromine, which I forgot the R. All right, so if I have 2 bromine, that is a -2. 1 magnesium is a +2. The 2 charges equal out, so it's neutral. So we have a methodology for doing this. So first, write the symbols of each ion side by side with the positive ion first. Right? So aluminum oxide, you have the aluminum first, oxygen second. Cross over the charge values as a subscript to use to indicate the number of each ion. So what does that actually mean? So let me draw it over here. So you have aluminum, Al, and we said it's a 3 plus, and oxygen is 2 negative. All right? So if I want to write a balanced formula for this, the easy way to do this is if I look at the 2, I'm going to take the 2 and put it as a subscript for its neighbor. And then the +3 for the aluminum, I'm going to use that as the subscript for my oxygen. And that's going to produce Al2O3. Excuse me. And so that's my balanced equation. So you cross the charges. And so now I can check it, make sure I'm correct. We said that aluminum has a 3 charge. So 2 times 3 plus, right, equals 6 plus. And then if you look at the oxygen, there are 3 oxygens times their 2 negative charge equals 6 negative charges. So the 6 plus and 6 negative, they actually equal out. So I've written this properly. Okay. Now, you want to make sure you have them written as the lowest whole number as well. So, all right, check the subscripts and divide them by their largest common factor to give the smallest possible whole number ratio. So when you write a formula, you want to make sure it's the largest whole common denominator for the subscript. So, so for instance, I have aluminum oxide Al2O3. Let's say that I wrote it, and I wrote it as Al4O6. So if I look here at this, can I divide anything by, if I look at 2 and 3, can I divide it by a common denominator to get it to anything smaller? No. However, if I had written aluminum 4O6, a common denominator, right? I have 2 and 3. So 2 will go in both, 3 won't. So if I divide 2 into 4, it equals 2. If I divide 3 by 2, 6 by 2 equals 3. So that's my lowest common denominator. So I've written this properly. All right, so Al2O3. Naming ionic compounds. Named by combining the name of the positive and negative ions. Name the cation first and then the anion. The ratios are not indicated by the name. And that can create a problem. But so if you look at Al2O3, the cation is aluminum, and the oxygen, the anion oxygen is oxide. So it's named aluminum oxide. Pretty simple. Now the stock system. So use to name elements such as iron that have 2 or more cations with different charges. So it distinguishes between the different ions. This system of nomenclature uses Roman numerals in the parentheses after the cation to indicate the charge. So for instance, we have iron, and you would name, there's 2 charges that can occur. +2 and +3 for iron. So let's say we divide oxygen with iron. We said that oxygen has a -2 charge. Okay, let me actually write with a 2 after. So you have it. So oxygen has a -2 charge. Oxygen can combine with either Fe2 plus or Fe3 plus. So let's combine them. So let's use what we learned so far. So Fe 2 plus, and combine that with oxygen and 2 negative. So we can write that. So if we do crossing the charges, we get Fe2O2. But now we need to check this to make sure we have the lowest common denominator. But if you look at Fe2O2, we can see from this that you can divide both by 2. And so we'll get FeO. Now, when we say iron, and we name it as iron oxide, but We need to indicate the charge of this ion because it could be Fe, it could either be Fe2 plus or 3 plus. So I'm going to write on here, right, iron, which is my a cation, iron, and I'm going to use parentheses, and I put Roman numeral 2, oxide. All right, and now let's try with the other ion. So we did Fe2O, Fe2. Let's use Fe3. All right, so again we have oxygen O2. Actually, let me try that again. All right, oxygen, we said was 2 negative. That's what I meant to say. Now we're going to use this ion. All right, so let's write the formula. So first what I'm going to do is I'm going to write Fe, right? And we said using the 3 plus, and then O, 2 negative. So I need to write the formula. So I'm going to take the charges, and I'm going to take this charge, the 3 from the iron, and use that as my subscript for my oxygen. And over here, the 2 negative for the oxygen, I'm going to use that as the subscript for the iron. So my formula is going to be Fe2O3. Now I'm going to name it. Now I use the 3 plus ion. So it's going to be iron, Roman numeral, 3, oxide. All right. So naming binary, we're done with this example. Now let's go on to naming binary ionic compounds according to the stock system. So I just demonstrated, but we're going to go through. I'm going to go through it again. So let's say we have CuCl2, right? So Cu has a +2 charge. Chlorine, Cl, has a -1 charge. I'm going to take the charges, the 2 plus, I'm going to cross it. So chlorine is going to be 2. This is understood to be 1. So it's be 1. I don't need to write the 1. So my formula is CuCl2. Let me try writing the Cl again. Okay, so it's CuCl2. So copper chloride. So name the cation first. Here the Roman numeral indicates the charge of the cation. You don't have to tell the charge of the chlorine. So the anion, you do not indicate the charge of the anion. Why? Because if I tell you what the charge of the cation is, you can figure out the charge of the ion, of the negative ion, the anion. Plus the name of the anion, right, equals copper to chloride. All right, so that's how we name your ionic compounds. So now we're gonna make this a little bit more complicated. We're gonna name compounds containing polyatomic ions. So what's a polyatomic ion? So let's define what that is first. A polyatomic ion is a group, right? A group of covalently bonded atoms with a charge. So the group itself has a charge. Name the cation first, and then the anion. So when you can actually have. So let me back up. When you are naming chemical compounds, right, ionic compounds, first of all, when you're writing it, you treat the polyatomic ion as if it was an individual atom or a monoatomic ion. And so we would do the same thing we just did when we were naming copper chloride or iron oxide. as far as crossing the charges. So example here is you have this, right? Silver, Ag is silver, and then nitrate. So we're going to name it silver nitrate, which is the nitrate one on the other side. So I named the anion first because silver has a positive charge, and then silver is a cation. Name a cation first, and then the anion, which has a negative charge. So this nitrate, that is a polyatomic ion. Aluminum sulfate, right? You have the aluminum, Al3, and then the sulfate, so another polyatomic ion. And when I name it, I name the aluminum first, because that's the positive one, the cation, and then I name the anion, the sulfate. All right. So this is a listing of so we have some common polyatomic ions. It's not all of them, but these are common ones. Now, if you are taking anatomy physiology, or taking a biology class, or you are interested in the health fields, you're going to hear these polyatomic ions because they are found in cells, and there's a number of chemical reactions that occur in the cell that include these ions. So you should become familiar with them. And we're going to use them in chemical bonding. All right, so some that you probably have heard or will hear. That's right, phosphate and phosphate. Phosphite and phosphate. You're going to probably hear sulfite and sulfates, carbonate, chromate. Probably hear cyanide because it's a poison. Nitrites and nitrates, right? So and ammonia, chloride. So these are some some polyatomic ions that you'll hear about in biology, other biology classes now in physiology or other biology classes. And then here's a couple more chlorite and perchlorate. All right, some more polyatomic ions. All right, covalent bonding. We mentioned covalent bonding already, but let's go over it again, and then we'll talk about the how you name them. So covalent bonding, chemical bonding, which occurs through the sharing of pairs of valence electrons between atoms to achieve a full valence shell, typically 8 electrons. And we said there are exceptions to it, but most atoms want to achieve the 8 valence electrons. And why? Because it's the most stable. If it's so again, there are exceptions, like hydrogen. We said that you only need 2 for it to be balanced. All right, so we mentioned already the octet rule. With a few exceptions, atoms will take part in bonding to achieve a full valence shell of 8 electrons. Bond formation. Bonds form as atoms approach each other, right? So as they get closer together. The distance between the atoms will determine the balance between attraction and repulsion between the atoms. Repulsion forces occur between the electrons and between the nuclei, and attraction forces occur between the electrons and nuclei. Initially, as the atoms approach each other, the repulsion forces are stronger than the attraction forces. And as the distance decreases further and the attraction and repulsion forces are in balance, a chemical bond forms, and potential energies are minimized. Electrons' orbitals overlap as a result of chemical bond formation. So let me just take a look at this for a second. So what we're actually saying. So when you look at atoms, right? So let's say I have, because it's easy, let's look at hydrogen. All right. So you have hydrogen. So this is the one proton, and this hydrogen atom, it's one electron, and then you have let's see if another another hydrogen atom. As they get closer together, the positive charges of these protons are going to repel each other, and these electrons are going to repel each other. However, the electrons are also attracted to the protons, so they are attracted to the protons. So you have to have a balance between these positive and negative charges. If they're too close together, then the repulsion forces between the electrons and the protons is going to be too strong, and your atom is not going to. So your atoms are not going to bond. So if they're too close, the repulsion forces will overtake the attraction forces. If they're too far apart, then the forces are just not strong enough to hold them together. So I have to have just the right distance between them in order for the bonds to form. And so if I do this, I'm going to actually show you the. Let's say that we use the cloud, the electron clouds to show bonding. We could show it this way, where there's an overlap over here, and that's where we have sharing of valence electrons between these two hydrogen atoms. If it's too close together, right? So you got proton there. If there's too much of an overlap like this, the repulsion forces between the electrons of the neighboring atoms and the protons, they're going to be too great. It's not going to hold together. So you have to have just the right amount of attraction repulsion forces. This is going to be the most stable distance. And how would you know the distance? You're not going to know the distance between the atoms. You'd have to look it up to figure that out. But just know that when bonds form, the atoms they can't be too close and they can't be too far from each other. They have to be just the right distance in order for the bond to occur. But when they do bond, like this is hydrogen H2, they are much more stable than they are as individual atoms. So hydrogen, as we mentioned before, hydrogen doesn't exist by itself. You're not going to see hydrogen ions move, in the air, typically. They're going to combine, right? They don't want to be separate like this. They're going to combine in pairs to form a more stable compound. All right, so that's bonding. Now, when you have covalent bonding, and we'll look at some examples. You can have single bonds, double bonds, and triple bonds between atoms. So let's go over the definition, and then I'll draw an example. So you can have multiple bonds, right? Multiple covalent bonds between atoms. Covalent bonds can involve one or up to 3 pairs of electrons. So you have single covalent bonds, right? And that's just a pair of electrons being bonded between two atoms covalently. Double covalent bond, that's when you have 2 pairs of electrons being shared between atoms. And the triple covalent bond, and that's when you have 3 pairs of electrons being shared between atoms in covalent bonds. And we represent it this way. Let's say we have carbon, and I'm going to move this. Let me move this over here like this. And let's look at carbon. All right, so you can have 2 carbon atoms bond together. And I'll put some hydrogens on here. And I'm going to focus on the bond between the carbon atoms. So this bond right here. That bond is actually a pair of valence electrons. So there's 2 electrons being shared between those atoms. So that's what we say when you see a single line, this is a single bond, a single covalent bond. And there's just one pair of electrons being shared. Well, one pair of electrons. Now we can have a double bond. And you'll notice here that I'm showing less hydrogens being attached to the carbons. And that's because if there's 2 valence electrons being shared between these carbon atoms, then I'm actually meeting the octet rule. So I don't need to have those other hydrogen bonds to meet the octet rule. So now I got these 2 lines, right? So each one of these lines represents a pair of valence electrons being shared between them. So I have, instead of so this is a double covalent bond. And again, let me stress that this is just covalent bonding, not ionic bonding. And you have 2 pairs of electrons in that bond. And let's look at the third one. A triple bond. Right? So I have 1, 2 pairs, 3 pairs of electrons being shared between those 2 carbon atoms. And you notice that because I'm sharing 3 pairs of electrons between the carbons, I only need 2 more to meet the octet rule. Remember, anytime you see a line, these are all pairs of valence electrons being shared. So all these, any line, so these lines, you only see those in covalent compounds, and they represent a pair of valence electrons being shared between those atoms. So whatever atoms are involved, or at each end of those lines, that's where you're going to see those electrons being shared. So this is your triple covalent bond. Okay, so there are 3 pairs of electrons being shared between those, and this is a very strong bond. However, when you have double bonds and triple bonds, because you have these electrons close to each other, there's repulsive forces. So it's a strong bond. However, it's not as stable as a single bond because you have these electrons. So if this molecule, right, if this molecule can change, can react to form a double bond or a single bond between the carbons, it will. How or would it want to be able to do that? I have to have more hydrogen atoms available. Okay. So that's multiple bonds, and you'll see this when we talk about carbohydrates, sugars. You'll see the carbon bonds between atoms, and when we talk about fats, lipids, you'll see actually double bonds in there. And you'll see that is the difference between saturated and unsaturated fats, is the presence or absence of double bonds. So let's go back to here. So we looked at single bond, double bond, and triple bond. Now let's look at naming binary molecular compounds. And this is easy if you compare it. So when we name them, we're going to use a prefix system. So prefix is just the group of words that you add in front. Okay? So prefixes are used to indicate the number of each atom in a compound. So like di means 2, or tri means 3. So rules, what are the rules for naming them? All right, the less electronegative element is the first given. So you might have to look at a table of electronegativities. It is given a prefix only if it contributes more than 1 atom to the molecule of the compound. The second element is named by combining the prefix, indicating the number of the second element, the root of the name of the second element, and then adding "ide" at the end. So let's look at some examples. Oh, I forgot O. All right, the O or A at the end of a prefix is usually dropped when the word following the prefix begins with another vowel. So, for example, monoxide and pentoxide. So these are the prefixes, right? So you have mono, 1 mono, 2 di, 3 tri, 4 tetra, 5 penta, 6 hexa, 7 hepta, 8 octa, 9 nano, and 10 deca. So these are the prefixes you're going to use. So examples, right? So you've probably heard, I'm sure you've heard of these. Carbon monoxide. So carbon's your first element, and then monoxide. So the mono is to indicate that you have one of it. And then carbon dioxide. So the Di is going to tell you have 2 of them. So you can see I got 2 oxygens here. So I put the prefix di. There's only 1 oxygen here. So I use mono for the prefix. Phosphorus tribromide. All right, so your phosphorus, that's the first element. Tri is indicating there's 3 of them. You can see over here in the formula, there are 3 bromine atoms. And then disulfide. So the first element, you only put a prefix if there's 2 or more. So you don't need to put mono carbon monoxide, right? Because there's only 1, so you don't put a prefix here. If the second element in a compound has 1 or more, I have to put the prefix. So disulfide decafluoride. So di is telling me I have 2 of these fluorine atoms. Sulfur atoms. And then deca is telling me I have 10 of these fluoride ions. So let me go back because I think I said that wrong. So disulfide, the di means there's 2 of these sulfide ions. Sulfide atoms, not ions. Sulfide atoms. And deca is telling me I have 10 of these fluoride atoms. All right. So here's another example. Dihydrogen monoxide. That's actually that is the actual name, the chemical name for water. Di telling you have 2 hydrogens. So there's 2 hydrogens. So I put the prefix di. Monoxide, a monoxide. All right, there's only 1 oxygen. Now, naming acids. And unfortunately, my table went on to the next page. But when we name acids can be defined in several ways. But for the purposes, it will be defined as a substance that when dissolved in water, it forms ions. So it's forming an aqueous solution, dissociates to produce hydrogen ions, and can donate protons. And the pH scale, pH is acids less than 7. 7 is neutral, and anything greater than 7 is going to be a base. So let me go over that for a second. What's an acid? Okay, so if you recall from your period, in high school chemistry, you probably talked about this. You have your pH scale. All right, so it goes from 0 to 14. And then this is 7. Anything less than 7 is going to be an acid. Anything greater than 7 is going to be a base. And really, the acid acidity is a measure of the hydrogen ions in a solution. So if you have an acidic solution, what it means is that there's more hydrogen ions than there are hydroxide ions, which are found in the bases. And then neutral, 7 is neutral, right? It's neither an acid or a base. And that's where actually you have the ratio of hydrogen in hydroxide ions is the same when it's an acid. And these are logarithmic numbers. So if you look at a pH of 0, that's actually 10 to the 0 power, and a pH of 1 is 10 to the first power. A pH of, so that's 1. A pH of 2 is 10 to the second power, and actually it's negative, sorry. I should have said that. Negative power, -1, -2. A pH of 3 is 10 to the -3 power. And so on and so forth, all the way down to 14. So a pH of 14 is 10 to the -14. So you can see there's a tenfold difference between each one of them. So if I go from here, from neutral, right, neutral this way, the acid becomes 10 times stronger each time. If I go from 0 towards 7, the acid is, you're going down by 1 magnitude. So how do we name acids? All right. An acid can be defined in several ways, but for our purposes, it will be defined as a substance that, when dissolved in water, forming aqueous solution, dissociates to produce hydrogen ions. Now, what does that actually mean? So we looked at the pH table, and I told you that this is a measure of the hydrogen ions. When you put an acid into water, and I'm going to use HCl, which is hydrochloric acid, which is something that you're probably familiar with. It's stomach acid. When I put acid into water, hydrochloric acid, what's going to happen in that water? So I got water in here. I put some of the HCl in here. It's going to break apart. So you have hydrogen ions and chlorine ions. So you have a whole bunch of them. And that's going to cause, the more acid I put in there, the more the more acidic it's going to become. So that's what we mean when I said dissociates, is that it dissociates so that the hydrogen and the chlorine break apart. So you see that with other acids as well. So you'll have the hydrogen that dissociates or breaks away when it's dissolved into water. And this can occur because of, as we've talked about before, water is a polar molecule, which allows these acids to dissociate. So naming rules, if we look at the naming of them, all right, the name of the acid is based on the name of the negative ion that is part of the acid. Acids made up of hydrogen, a positive ion, and a negative monoatomic ion. So this table is an example. Let's take a look at that. So if you look at this, all right, so if you look at that table, all right, so you have the acid here, HF and HCl. So you have these two acids. The hydrogen is the positive ion in both cases. The fluoride ion is negative, and the chloride ion is negative. Should be, and then so that's the name of your the name of the negative ion is fluoride for your F, fluorine, and then chloride is the negative ion. And so we can use that to measure how do we name these acids? So if acids contain a negative ion ending in IDE, remove the suffix IDE and add this suffix ic. All right, so we have in both cases we have the fluoride, and what I'm going to do is I'm going to remove the IDE and I'm going to replace it with ic. Okay, so fluoric. And then chloride. Okay, I'm going to remove the IDE and replace it with IC. All right, so IC. Let me try that again. All right, so chloric. So down here, you have the negative ion, the fluoride. I'm going to remove the IDE, okay, and add the IC. So you have hydro, which is the positive ion, the hydrogen. You have the fluoric, and then add the word acid after. HF, right? So we said that the fluorine, the ion is fluoride. I'm going to remove the IDE, and I'm going to add IC. So hydro for the hydrogen, which is the positive ion, plus the fluoric acid. So hydrofluoric acid. HCl, remove the IDE and add IC. You have the hydro for the first element, hydrogen. So hydrofluoric acid. Okay, so now that we went over these, let's go back to this and just review this for a second before we move on. So what we did when we named these, so if acids contain a negative ion ending in "ide," remove the suffix "ide" and add the suffix "ic." So that was what we did here when we went from fluoride to fluoric. We went from chloride to chloric, and then add the prefix hydro. So the hydro, we use that. So you only use hydro prefix if the acid contains a monoatomic ion ending in "ide." All right. So these are some other examples. All right. So you will see here the acids, the positive ions, and the negative polyatomic ions, and the name of the polyatomic ion. So these are polyatomic ions here. These are the names of them. So you have nitrate, sulfate, sulfite, nitrite, phosphite, and phosphate. If the polyatomic ion ends in 8, ATE, remove the 8 and replace it with IC and add the word acid. So let's look at these. So we have nitrate, sulfate, and phosphate. So these three are going to be, or you're going to use the rule when you name it acid with nitrate, sulfate, and phosphate. So again, if the polyatomic ion ends in 8, remove the 8 and replace it with IC and add the word acid. So here you have nitrate. I remove the 8. I'm going to replace it with IC and add acid. So now I have nitric acid. Sulfuric acid requires an additional step ending in 8 is replaced with IC, but UR is added before the IC ending. So you have this sulfate, right? I'm going to remove the ATE. I'm going to put UR and IC, and I get sulfuric acid. Phosphoric acid requires an additional step, right? I'm going to remove the 8. I'm going to put the UR and IC, phosphoric acid. If the polyatomic ion ends in "ite," the "ite" is replaced with the ending "aus" and acid is added. So I have a nitrite. So this is my polyatomic ion nitrite. And if I name it as an acid, if it's an acid, nitrous. So I got rid of the ITE. I added "aus" and added acid. So nitrous acid. Sulfurous acid requires the additional step as well. The ending is "ite" replaced by "aus," but UR is added before the ending "aus." So sulfite, sulfurous acid, sulfurous acid. And phosphorus acid also requires an additional step. The ending is replaced with "aus," but UR is added before the ending "aus." So you have the polyatomic ion phosphite, phosphorus acid. So phosphorus acid. All right. So using chemical formulas, I'm going to go over this in another video, but we will touch on that. So I'm just going to stop here. We will do practice problems for naming different chemicals. Yeah, because it just takes practice to learn it. Okay, thank you.